Hello everyone, welcome to this AOS-CX 10.10 update, and the topic is the campus shared border VTEP between EVPN Fabric. That is how to share a border VTEP between Fabric. My name is Vincent Giles. I'm part of the technical marketing engineering team inside the Aruba switching organization. So as a traditional agenda of those updates, we'll go through an overview, the use cases, details, configuration, best practice, and a little bit of troubleshooting. So let's start with first some acronyms definition. So you have that already in other updates that we did in the past. So, but as a reference, this is good as acronyms can be quite difficult to understand sometimes. What we did in the data center in the past of that was 10.09, we qualify multi-fabric with a dedicated border VTEP per fabric in each fabric. So in the data center, you see here that there is blue tunnels between border VTEP. So that is definitely not a use case for the campus where typically it's not easy to have dedicated border for each fabric. Instead, we already discussed in another update for 10.10 this topology where we have a collapsed core aggregation VS6 pair that is acting as a border VTEP per fabric. So we already covered that aspect, which is the border VTEP as a route reflector. So please see in the YouTube channel, you have this as well. And then this time, in that particular session, we want to cover the core box that act as a shared border between fabrics. So in that example of site 1, you have two fabrics, and each fabric share the same core border as a border VTEP. So this is that scenario that we want to cover. So let's go to some overview of this. So what was 10.09 again is that dedicated border was per fabric, and that was mostly a data center use case. So there were no support for a shared border. And especially in the consideration, there is L2 extension and L3 VNI. So let's, you understand where I'm coming for that. In 10.10, there is no new feature. It's not a new feature. There is no new command. There is nothing new in terms of development and code. This is purely a campus solution validation and fully supported based on the test that we made. However, it means that it's limited in terms of functionality in the sense that it's only layer 3 VNI. So between Fabric 1 and Fabric 2, we won't have L2 extension. It's purely routed. So let's go to the use case. That's what I'm explaining. Only L3 VNI. So, and I'm going to, so pay attention, I'm going to use stretch VLAN and stretch subnet interchangeably in this presentation, right? So consider that when stretch VLAN, this means as well stretch subnet and reverse. So unlike the data center where you've got a lot of VLAN extension, right? In the main campus use case requires less VLAN extension between fabrics. I'm talking about between fabrics. So in the same building, you may want to have stretch VLAN, but between buildings, maybe not necessary to have a VLAN extension. Of course, there will be always exceptions, but most generally speaking, it's less an issue to have VLAN extension between fabrics in the capacity in the campus multi-fabric use case than in data center. So the 10.10 scope is really limited to layer 3 VNI and no L2 VNI outside the fabric. So this is due to the current method that we have to tune the VXLAN split horizon rules that we have in the EVPN configuration. Remember, in 10.09, we introduced the dynamic VXLAN tunnel bridging IBGP to EBGP in order to have separation of broadcast domains so that we can bridge them together, right? So we were able to receive internal BGP EVPN routes through an intra VXLAN tunnel and push it back to an external interfabric VXLAN tunnel. So that was thanks to this command. Well, obviously, we don't have external to external or internal to internal. So in future, a new knob that is independent to internal versus external is to be investigated so that in future we want to support L2 VNI. But for the time being, this is L3 only. And when there is a need specifically for a customer to have L2 extension between fabric in the campus, then we have to put in place a dedicated border. In terms of topology, and just to analyze what it means. So access here, aggregation here. So typically the aggregation are interconnected, and you have core here. And you see the core is in VS6. So you'll find what something that is, I would say, counterintuitive, that all the circuits are layer 3. And in legacy architecture, you have the aggregation layer that is a VS6 with L2 to the access. And you have upstream L3, and the core do not need to be VS6. The core is, most of the recommendation is to have the core being a standalone layer 3 box. Here, you make the reverse. The core must be VS6 because right now our implementation of multi-homing is leveraging VS6 technology. So for the multi-homing on the border, we want to have yes, multi-homing. So this is a VS6 pair of switch, core 1 and core 2. The aggregation are non-VS6, so these are just L3 box. So here, this is not a VS6 ISL. This is regular routed lag here between AG1 and AG2, and all the circuits down to the access are layer 3. So obviously, I took an example to make the opposite of the regular legacy architecture. If you need L2 because of some local needs here, you can also have a SVI for transit VLAN over an L2 aggregation. And there is no problem. This is pure underlay. But for the overlay, this is completely transparent. This underlay is completely transparent. It can be SVI over L2, or it can be routed only port. So what we have in terms of overlay and VXLAN tunnels between the VTEP of the same fabric, so that's the same full mesh capability, and between the VTEP for the traffic to the other fabric on the same side, then you will go through the border. So the border would be, I would say, the proxy for reaching any other fabric, including the one on the same side. So between building 1 and building 2, you will see that the VTEP 1 tunnel is constructed to the border, and then from the border to the other VTEP of fabric 2. Similarly, for other sites connectivity, so site 2 and site 3, you will use those blue. However, this one for VTEP 1 to the border is limited to L3 VNI, whereas the one between the VTEP inside the same fabric can be L3 VNI and L2 VNI. Those tunnels between VTEP of fabric 1 and VTEP of fabric 2 are unnecessary and unwanted, right? So in terms of traffic, between fabric 1 and fabric 2, you will use 2 tunnels. So this one here to the border and this one from the border to the other VTEP. So maximum 2 tunnels between inside the same site that share the same border, core border. And between the fabric in one site to another VTEP in another site, you will use probably 3 tunnels. So this one here to the border, then the blue between the 2 sites, and then another orange to the final VTEP. So what happened in terms of BGP session for the control plane? You have the same intra-fabric BGP session than before for exchanging routes and for servicing L2 VNI and L3 VNI. For interfabric, you will use external BGP. So that's between the route reflector in building 1 and the core border, shared border, and between the core shared border and the building 2 here route reflector. And then obviously that external BGP session as well to site 2 and site 3. So what you see immediately is that this core border runs another autonomous number than the building 1 and building 2. So fabric 1 and fabric 2 get their own autonomous number as well. Core is running a different autonomous number. Similarly, you've got BGP EVPN here that is over the loopback typically. Next is what I mentioned before. What about an IBGP VPN sessions between the two? Again, you don't need that because you are here. What we have in EVPN is setting next up that are overlay destination IP that do not require a continuity in the host for that specific destination, because the destination IP is the VTEP IP address, which required a continuity in the underlay. So the underlay routing is very important, as we'll see in the next slide. So no IBGP VPN session between the route reflector as of before, OSPF as before explained, and eBGP IPv4 RS family to exchange the route and the usual cross redistribution between BGP and OSPF. So nothing really new in that aspect. The objective similar than before, right? So this is to make sure that so typically what we want for, let's say, VTEP 10 here. So that core border that want to reach the routes and the destination in autonomous number 1. We want to have that VTEP, that destination being VTEP 1. We want to build that tunnel here, which is in orange, dark orange. And similarly, for, let's say, access 3 to access fabric 2, we are the other side. We want to have a VTEP 3 receiving all those routes that are not inside fabric 1, with the next stop being VTEP 10, right? So what we do for that is playing with next stop self and next stop exchange similarly than before. So you see that you have the ability here to play with that. So no, we will not do an internal BGP session modification with next stop self. Why is that? Because again, we want to preserve the next stop. So the intrafabric route reflected with the originator access VTEP. So this is what we have. So VTEP 1 will receive the route of access 3 with VTEP 3 next stop. So that is normal. However, the next stop self toward the IBGP speaker is not used, so that the shared border core IP address as a next stop can be kept. Otherwise, the route reflector will override that with next stop self command. So we don't use next stop self command to maintain those EVPN routes entry coming from border core 1, VTEP 10, same IP used as the next stop for VTEP 1, VTEP 2, and VTEP 3. So they will receive IP address of the border VTEP instead of the IP address of the route reflector for the next stop. And then what happened for the advertisement from fabric 1 by the route reflector to that border? So what we use is the next stop unchange command on the peering. For similar reason, we want to preserve the next stop that is coming from the internal fabric. So VTEP 1 must be preserved in order to construct the tunnel as well to the border. And similarly, here, what we want to have the border resetting the IP address for next stop for anything that is outside, right? So all the route advertised by the border should be with the VTEP IP being VTEP 10, the VTEP of the IP address of the border. So detailed caveat, so no new command. Everything has been already validated. Next up change, unchanged command has been validated in the past. So this is just a pure solution validation. Again, support for V4 and V6 unicast overlay, but not public claiming. Just a note that, as I mentioned before, it's in contrast to the legacy architecture. Here you've got the aggregation layer, which are pure standalone layer 3 nodes, right? And the core requires VS6 for VTEP high availability and dual and multi-homing. I mentioned that if you have, for legacy reason, any kind of L2 between access and the aggregation layer, you can still use that, and a transit SVI for reachability of the loopback between the access and the route reflector, no problem. The aggregation devices are interconnected for IGP continuity. Okay, so this is important. And typically, it offers flexibility for the campus. Remember, in the data center, the spines are not interconnected because you know for sure that there will be connectivity between every leaf to every spine. However, here in the campus, you may have some fiber constraint. For instance, there is a single home, there is a single fiber to an access. It can happen. You do not master much what happened in the campus. Or you may have a dual fiber, but only on one aggregation box. Even if the customer knows about that, it can happen because of constraint, multiple constraints in the campus. So it gives you a lot of more flexibility to have that interconnectivity between aggregation 1 and 2. The route reflector function is hosted at the aggregation layer, so we saw that. The L2 VNI routes that are exchanged between the VTEP and to the route reflector are also exchanged everywhere. So you may say, well, those routes are useless because we are not doing L2 VNI between Fabric. So Fabric 2 will receive L2 VNI routes of Fabric 1. So any route type 2, for instance, will be received. You may say, well, this is not optimized. Those routes are not programmed into the ASIC because we are not using L2 VNI in the data plane, right? So it will consume few additional resources from a control plane perspective. Yes, we know about that, but putting in place some filtering for those VNIs might be a bit cumbersome. So yes, there are some software resources used, and you will see those routes, even if they are useless in the other fabric. But this is a good threshold that a good balance and trade-off that we found. The type 3 optimization that I talked about in the previous presentation is not needed and not performed. So that being said, if there is a need for VLAN reuse, let's say the customer wants to use the same VLAN 10 in Fabric 1 and in Fabric 2, and having the same numbering convention for numbering the L2 VNI. So let's say 10,010 for VLAN 10 in Fabric 1 and in Fabric 2. You end up by the same VLAN ID and L2 VNI ID in Fabric 1 and Fabric 2. But you do not want to exchange those routes because L2 VNI is not supported. So for that, you have different route target, right? So you ensure that we have different route target used inside Fabric 1 and inside Fabric 2 so that those routes are not exchanged. And remember, type 3 route optimization is not done. So that's why it's important to have different route target. So these are in 10.9, we define local scope route target and global scope route target. A local scope is for the local fabric only. So as a matter of fact, this use case for campus shared border VTEP is for no L2 VNI. So the route target for L2 VNI is local to the fabric. So that value is not the same in the other fabric. So in that perspective, there is no problem. If it happens that for whatever reason, the route target value cannot be different, in that case, different L2 VNI values should be used among the fabric. But again, that would be very unlikely because different route target for that use case is not at all an issue for the configuration and the design. Use case and the qualified platform. So this is 64, 8325, and 8360. The validated multidimensional scale here, you can see that for those 3 platforms with the profile, we qualify up to 64 VTEP per fabric. Number of fabric is 32. You have the routes, L3 route across all VRF. The overlay hosts that are used, so that are also qualified with dual stack. The overlay host across multi-fabric, this is not needed because we just have L3 VNI between fabrics. So this is route type 5. So not supported to have route type 2 between fabric. The data plane, as I mentioned, will not support that. The VLAN local to the fabric, there is no stretch VLAN. Again, L3 VNI only. I do that multiple times in the table on purpose just to remind it's L3 VNI only. And we have up to 32 VRF qualified for that multi-dimensional scale. Configuration, nothing new, as I mentioned, but that's a good summary here that you have in blue. So that's at the aggregation layer route reflector, right? So you will have to the core border, you will use next stop unchange, and I take time to read that. The next stop of IBGP access VTEPs must be retained so that on the border, the shared border VTEP, the VXLAN destination VTEP are the access VTEP and not the route reflector. So this is the purpose of that command. For the leaf, so the route reflector sending BGP route to the leaf, the access VTEP, the next stop self command is not used because we want to retain the IP address as a next stop for the border. Okay, so this is explained in blue here. So you have a summary of the reason of those 2 commands. So do not use next stop self. So for configuration, for everything else in terms of underlay routing and so on, again, 10.09 is the right place to go. Best practices. Shared border VTEP must be a pair of VSX for reliability. It's not. It could be working with only one node for sure, but not in operation. Aggregation switch should be interconnected for OSPF continuity. I touch on it. And again, if there is VLAN ID reused and same L2 VNI ID reused, please use different route target value between fabric. So do not use global scope EVPN route target because there is no L2 stretch. Here, this is really for EVPN section. For VRF section that is about the L3 VNI, obviously you want to share the L3 VNI route per VRF. So the route target would be a global one, but not for the route type 2 and the EVPN routes related to L2 VNI. Troubleshooting. So you again, please check that the next stop unchange command is properly configured on the aggregation route reflector back to the border core. On the access VTEP, you will obviously check that the next stop VTEP IP of the external fabric is retained with the core border VTEP. And this is what we were explaining. And you will check that as well, thanks to the, you can do an include with the IS number for the other external route. And you will check the router MAC as well, and the router MAC is preserved. Some resources. Please get through the update of the user guide for VXLAN for 10.10. As well, I would say that the 10.09 deep dive that we did in the past for EVPN VXLAN multi-fabric is very useful to understand all the concepts that we talk in that session. With that, thank you very much for your attention.